we are going to learn how we are going to approach a particular coding problem. So this will be a generic way, so that this generic way we are going to use throughout all our videos in solving a particular coding problem. So let's suppose we are solving a problem X. So what will be the approach of solving that problem? So we will be discussing in depth about how we are going to approach a particular problem. So before we are going to start and let's start solving one of the problem. Before that, you should have at least knowledge of one of the programming languages, including C, C++, Java, Python, and others as well, because it is required, because you have the basic knowledge of loops and other things that we are going to solve a particular problem. So with all those things, let's get started with the today's problem. So today's problem that we are going to discuss and we are going to solve that problem is finding a particular number is a prime or not. So if we talk about prime numbers, I think most of the guys about the prime numbers. So prime numbers are those numbers which has exactly two factors. What do you mean by factors? Is like exactly two numbers, is this particular number n is exactly divisible by two numbers only. So if we take example, for example, we can take it as 2, 3, 5, 7, 11, 13, and many more. So if we talk about 2, you can see that 2 has a factor 1 and 2 itself. Again, 1 and 3. For 5, it's 1 and 5. For 7, it's 1 and 7. For 11, it's 1 and 11. For 13, it's 1 and 13. So all these numbers have exactly two factors. Which are these factors? Is 1 and the number itself. The number itself. So it has exactly two factors, including 1 and the number itself. Now, the question is to find if a particular number n, I will write down the question, find if a given number n is prime or not. So before we start solving this problem, the first very approach is to think like how we are going to code this problem. So if we look at, if we ask ourselves, let's suppose we are given a number n, let's suppose we are given 13. So how will we approach this problem to solve that 13 is a prime or not? So to be a number to be a prime, we know that it has exactly two factors. So if it has more than two factors or less than two factors, then it is not a prime number. So the first approach of ours is to calculate the number of factors. So let us start with the 13. So we'll ask 1. Yes, 1 is a factor. So we will keep our count as 1 currently. Now we will say 2. No, 2 is not the factor. 3 is also not the factor. Then we move to 4. 4 is also not the factor. Then 5 is also not the factor. Then 6, it is also not the factor. 7, it is also not the factor. Similarly, 8, 9, 10, 11, 12, all of these are not the factor. Then we move to 13. Yes, 13 is the factor, so we move to count to 2. So we will say that the number of factors count here is 2. So we can call that 13 is a prime number. Okay. So let's just give a basic, let's do the code for this. So here is what you have to have the basic of codings, for loops, conditionals, and all those things. So let's just start with the problem. So let's take a variable that is called count. We will take in count as 0. We will keep that as 0. Now we will start a loop. We will say I equals to 0. I is smaller than equal to n. N is a number for which we have to find if it is a prime or not, and then we will increment the I. Now we will check what we need to check from 0. Starting is 1, not 0. My mistake. Let's just remove this and take it as 1. So from 1 to n, we will check if that value of I is a factor of n or not. So we will check if n modulo I double equals 0. So if this is the condition, then what we need to we need to increment the count. So we are basically saying that yes, I is a factor of n. So we will increment the number of factors count. At last, we will say if count is equals to, we know it has exactly two factors. We will return true, else return false. So one thing I would like to say that this is a basic like approach. Just I am saying you can use any of the programming language to code this, but this is just a a rough code, a pseudo code kind of you can call that I'm providing to you. You can code this in any language. So now looking at this code, we can provide any value of n and it will return it whether it is a prime number or not. So now we have the code of basically checking if a number is prime or not. Now we need to understand how much time it is going to take to execute this program for different inputs, smaller inputs, larger inputs. But for a rough estimate, we can say that its time complexity is big of n. That why it is big of n, we will discuss in the later videos. Just for now, say that time complexity is big of n, and we will also learn what is time complexity. The space complexity is big of 1. We are not using any extra space. The same thing goes to here as well. I will discuss this in depth in the other videos about the space complexity and the time complexity. Now, let's suppose here we are providing 13 as an input. So let's suppose n equal to 13. So it will be running 13 times. Okay. Because if you check our loop, it is kind of running from 1 to 13, 1 to n, so it will be running 13 times. If our n is equals to 100, it will be running 100 times. If n is equal to 10 to the power 8, it will be running 10 to the power 8 times. The iterations will be running, yeah, like this is the iteration, and it is the value of n. So if, we can see that as our input grows, the number of iterations are also increasing. So let's suppose now, let's suppose for a rough estimate, and we can say that in 1 second, the machine is performing 10 to the power 8 iterations. Okay, it is performing 10 to the power 8 iterations in 1 second. So if n is equal to 10 to the power 8, the machine will take 1 second to execute the whole program. That's fine. 1 second is a good number. But let's suppose now further increase. Let's take n equal to 10 to the power 9. Okay. So the total time, just a minute. So the total time will become 10 to the power 9 by 10 to the power 8 second will be equal to 10 seconds. So now if we are taking a number which is 10 to the power 9 to find it is a prime or not, 10 seconds will be taken by the machine to execute the whole algorithm. Now this is fine, 10 seconds is fine. Now let's suppose there is again a larger input. If we're taking more than this, again a larger input, let's take n equal to 10 to the power 18. So this is a very large number. Now let's calculate the time taken by it. So if we say one iteration, if we say 1 second equal to 10 to the power 8 iterations, so we can say that one, just a minute, one iteration will be equal to 1 by 10 to the power 8 second. So one iteration will be done in 1 upon 10 to the power 8 seconds. Now let's move, take then what is happening here? Then 10 to the power 18, 10 to the if n equal to 10 to the power 18, so 10 to the power 18 iterations will be done in 10 to the power 18 divided by 10 to the power 8 will be equal to 10 to the power 10 seconds. And if you calculate this, 10 to the power 10 second is approximately equal to more than 300 years. So do you think that if you execute this algorithm, do you think you will be alive to watch the result if 10 to the power 18 is a prime number or not? No, not at all. So this is a very huge number, and here it is a time where it came up. We need to optimize our solution. So optimization basically take place not for a shorter period of not for the shorter inputs, but what if our input goes big? So why we think about this is because whenever you are creating any algorithm, you need to think about larger inputs, how your algorithm is going to perform on the larger inputs. So now we need to optimize this solution so that our algorithm perform optimal for larger inputs as well. So let's see how we are going to optimize, how we are going to find some key facts in the problems which will lead us to a optimal solution. One of the factor, that is I. So are you able to find another factor if you know one of the factor? Yes, it can be possible. So other factor will be n by I. So for example, let's take 12. So what are the factors of 12? We can write is 1 and 12, and we can write 2 and 6, 3 and 4. Okay. So if we know one of any of these factors, we can find the other as well. So now using this example, let's take an example of 24, n equal to 24. So we know that there is a I, there is n by I, and here is our n. Okay. Now let's take n as 1. N by I will be 24. Number is 24. Now 2, n by I will be 12. And this is 24. Now take 3, it will be 8 and it is 24. Then 4, then 6, and then 24. Okay. Let's make all the possible pairs. So now we will come to the 6, 4, 24, 8, 3, 24, 12, 2, 24, and then 24, 1, 24. Okay. Now this is all the possible pairs we have made you for the 24, all the possibilities of all the factors we have. Now if we look closely at here, what we see that from 1, 2, 3, 4, this is again repeated here. You can see after this it is again getting repeated. So what does it means when we are kind of checking for 24, how many pairs, how many factors are there for 24? We can see that after a particular time, after a particular values, the factors are getting repeated. Because if one here is 1, 2, 3, 4, after which we say that again 1, 2, 3, 4 is coming, and again 6, 8, 24 is coming. So what does it mean? It means that we no need to check all the factors from 1 to n to find if it is a prime number or not, or what are its all factors, if the count of factors is greater than 2 or absolutely equal to 2. So we don't need to check all the factors. So but there is the thing where we need to stop, so that there must be a number after which all the factors will be keep on repeating. So we need to find that. So from here, if we check this relation, after which you say after 4 and 6 they are again repeating, 6 and 4, 8 and 3. So what does this relation say? So this relation means we have to stop where I is smaller than equal to n by I. If you closely look, the relation is whenever we have to stop where I is smaller than equal to n by I. And if we take this I to this, we can see that I multiplied by I is smaller than equal to n, or we can say that I is smaller than equal to root of n. So this relation we have found from this observation, that we observed by finding the factors, and we see that all the factors keeps on repeating after a certain time, and that certain number or time is after coming is whenever I is smaller than equal to n by I. So if I is increased by n by I, then we conclude that the factors are repeating. So after solving this equation, we found that I must be smaller than equal to root of n. Now what we are doing here, we are doing is like we are only checking the number of factors till root n. For example, if we have a number 16, if we have a number 16, then we don't need to iterate from 1 to 16, but we have to only iterate from 1 to root of 16, that is equal to 4. So you can see how much reduction we have done using some key facts from the problem, that we first analyzed that any of the numbers that are made is any of the factors always occur in pair. Then we find a relation between both of them, and the relation comes up to is I is smaller than equal to n by I. Now let's calculate the how much time it is we have reduced after forming this equation, that we are only traversing from 1 to root of n and not from 1 to n. If we are using our previous algorithm to solve, the time taken was 10 seconds. How it comes is like we have thought like 1 second, it our machine is solving 10 to the power 8, doing 10 to the power 8 iterations in 1 second. And if we are wanted to do 10 to the power 9 iteration, so the total time will be 10 to the power 9 divided by 10 to the power 8, which will be 10 seconds. So this was with our previous previous algorithm. Now, with our new algorithm, if we have to do 10 to the power 9 iterations, it will be equal to root of 10 to the power 9 iterations. So let's calculate. The time will be equal to root of 10 to the power 9 divided by 10 to the power 8, will comes out to be, let me just make it big. Yes, now it will be equal to 10 to the power 5 divided by 10 to the power 8. It will be equal to 10 to the power minus 3 seconds. You can see how fast. Previously, we were spending 10 seconds, and this is now 10 to the power minus 3 seconds. So we have done a huge reduction by only observing few things in our problem, optimizing the solutions, and providing an optimal solution. Now, I will not code this. You can code this algorithm on your own, or when we are doing this kind of questions in our data structures and algorithms other playlists, we will be solving this question with a proper doing the code on a code editor. But for now, the key thing to learn here is that any problem we are solving, we must do some basic observations over the question and try to optimize it further. In this way, we need to solve any problem. We start with a brute force approach, then we slowly move down to some observations in our question, and then we provide an optimal solution. So that's all for this video, and hope you like this video about how we are going to optimize a problem, how we find the key facts or some observations we will do in our questions. And in the next video we will talk about the time complexity, what is it, how to calculate the time complexity, how to find the space complexity and all. So thank you for watching this video. We'll be back in another video. For now, thank you. Bye bye. Have a nice day.